All right, here we go. So let's talk about algebra a little bit. We can typically, when we do algebra, aside from the imaginary numbers that we do sometimes, we compute and do algebra with real numbers. You know, exponents, operations, multiplication, division, raising something to an exponent, using variables and constants. We do algebra, and we also have expressions, right? Can someone give me an example of an expression in math? Let me ask you a different question. Can you give me an example of an equation? Y equals x. Awesome. Okay, so can you give me an expression? Sure, x plus 3. 17 minus 4x, right? All an expression is just either one or more constants or variables with no equal sign. Well, the thing is, we can also have trig expressions, and I apologize for the crazy blinky screen that'll happen sometimes. And what that means is all of our trig ratios are matched on the unit circle, and those are also real numbers. So we can make expressions and make equations using trig values. So for instance, how do you find the cosine of a coordinate on the unit circle or of an angle? So x over r, and if you're in the unit circle, r is 1. So it's just the x coordinate, right? So what is the cosine of x if x is 0? What is the cosine of 0 degrees? Try again. The x value at 0 degrees. It's just 1, right? So instead of writing 1, I could write that as cosine of x. And I could do more. I can write cosine of x, which is 1, minus 0, which was x, right? Which would still be just 1. So that's just an expression. You can also divide. So you can say 1 minus the secant of a over the tangent of a. That is another example of an expression. And the most useful one for us today is going to be exponents. So if I do the sine of x squared plus the cosine of x squared. Now, as this is written, it actually looks like what I'm not trying to say. This looks like the sine of x squared all together. But what I'm actually trying to say is the sine of x times the sine of x, and the cosine of x times the cosine of x. But instead of using parentheses in trig, what we do is we put that exponent in between the function and the angle. So we say that that is sine squared x plus cosine squared x. So this is the preferred, these are equivalent, but this is the preferred notation when we square trig functions. Okay, so let's we're not going to define much, but let's define our first word. A statement of equality that holds true for all values is called an identity. A statement of values that hold, or a statement of equality that holds true for all values is called an identity. What is the multiplicative identity in math? The multiplicative identity. Well, that's like commutative. So that's just kind of switching the numbers. The multiplicative identity is different. What does the word identity sound like? Or what does it mean? If I say this, I'm going to give it away, but since you're not close. what number do we multiply anything by to get itself? 1. That is a multiplicative identity. So we can say that, for an example, we can say n times 1 is equal to n, right? No matter what we multiply a number by, no matter what number we multiply by 1, we will always get itself. What is the additive identity? Say again? That is true. That is true. But it's not the additive identity. But I'll write it. N plus n is equal to 2n. The additive identity is what number do you what number do you add to something and get itself? 0, right? So n plus 0 still equals n. N plus 0 equals n. Now let's do a little bit more algebraically complicated ones. How can I expand a plus b squared? What's another way for me to write that? No, lies. Closer. There it is. A squared plus 2ab plus b squared, right? Because this is a plus b times a plus b. Don't forget those two middle terms, ab plus ab. What about something like x squared minus y squared? Oops. You don't need parentheses around it. I don't know why I did that. That's okay. How can I expand that? Fabulous, Zach. That's just using your difference of two squares factoring method. Okay, these are algebraic identities. They work for no matter what values we have for a and b and x and y and n, it will stay true all the time. Okay, now not everything is an identity, and in fact, it's kind of difficult to prove that something is an identity, that it works for every single case, because you cannot, we have an infinite amount of numbers, so you can't sit down and prove that, if I plug in 1, then it works, and then if I plug in 2, it works, and if I plug in 3, it works, and you have to prove it for every single case. So proving something is kind of difficult, but disproving it is a little bit easier. Does the word counterexample ring a bell from geometry? Nope. It's okay. A counterexample is an example to disprove something, or to prove that something is false. So to prove something's true, it takes a lot of effort. To prove it's false, you really only need one example to show that it doesn't work, and then there's that, right? So let me give you a statement. Every teacher who works at Gregory Portland High School teaches from his or her classroom. True or false? Give a counterexample. Me, right? I'm not there, but I still teach. Okay, so I'm going to let's do an example. I want you to suppose, let's say prove whether or not sine of x times the cosine of x is equal to the tangent of x is an identity. So I want you to prove that this is true for all cases, or that you give me one example to show that it's actually false. And I'll give you a hint. We're not going to start with our proofs today. We're just going to get comfortable with our identities. So I'm just going to look for a counterexample to this equation. So here's one approach. If we suppose that x is equal to 0. X is equal to 0. Now, on the unit circle, that's this point right here, right, at 0 degrees. What's the coordinates at that point of 0 degrees? 1, 0. So what I'm going to do is I'm going to plug in the sine of, and instead of x's, I want to know what the sine of 0 times the cosine of 0, I want to know if that is equal to the tangent of 0. If it is equal, then that means it works. If it's not equal, then I've found a counterexample. All right, so what is the sine? How do you find the sine of something? Y. So the y value for this coordinate is 0. We find cosine by the x value, which is 1. So that'll be 0 times 1. I want to know, does that equal the tangent at this point? How do you find tangent? Y over x, which is, what's another way to think about tangent? Oh, interesting. We're going to get to that in a second. But slope, yes, is the one that I'm looking for. So it's y over x. Cosine was the x, sine is the y. So if we think about it as slope, or just doing y over x, that's going to be 0 over 1. So is this a true statement? Yeah, 0. Oops. 0 does indeed equal 0. So what that means is you haven't proven a doggone thing. You've plugged in something and it's true, but you haven't proved it works for every case, because in order to do that, you'd have to do a lot more than just plug in a value. We're trying to find a counter example though. So now I want you to suppose, what if x equals pi over 4? So on the unit circle, pi over 4 is at this point right here. What is the coordinate point at that point? Fabulous. So that's what I'm going to use for x and y. And we're going to do the same thing. We're going to substitute in those numbers for x. So the sine of pi over 4 times the cosine of pi over 4. I want to know, is that equal to the tangent of pi over 4? Again, we find the sine by using the y value, which the y value at this coordinate is square root of 2 over 2. Cosine is found by the x value, which is also square root of 2 over 2. And what is the slope of that? Yeah, right, exactly. You can write either. You could write square root of 2 over 2 over itself, or just know that that converts to 1. All right, so let's simplify. Square root of 2 over 2 times itself. In the numerator, square root of 2 times the square root of 2 is 2. In the denominator, 2 times 2 is 4. 2/4 is not equal to 1. Therefore, this implies that you have shown that pi over 4 is a counterexample. Okay, so pi over 4, and the screen's going to get very blinky because I'm about to write a lot, so bear with me. Pi over 4 is a counterexample. Counterexample to prove sine of x times the cosine of x equals tangent of x is not an identity. So all it takes is one example to show that it does not work, and you have proven that it is not an identity. You with me so far? Okay. Now, let's go ahead and define our trig. Is that a question? Oh, okay. Just checking. Let's go ahead and define our trig functions. So we've been using this already through our notes, but just so things are clear, I want to define sine of theta, cosine of theta, and tangent of theta in the unit circle. So you guys have already told me that sine is found by doing, Zach said earlier, y over r, but again, you may assume that this is all unit circle stuff, so that's going to be y over 1. Therefore, the cosine is, well, Ms. Schwanier, the cosine is x over 1. And then tangent, y over x. Okay, but these are not the only 3 trig functions. What else do you have? Very good. Cosecant, secant, and cotangent. How do you find these? Yeah, the mathematical word there would be reciprocal. So if we take the reciprocal of the sine value, this one is 1 over y. Secant is 1 over x. Cotangent is x over y. So those are our trig definitions. Now, if we're going to use these definitions to come up with multiple identities, reciprocal identities, which means these work for every single angle on the unit circle no matter what. So this reciprocal identities, you can write these on your orange reference sheets. Can you help me to write sine in terms of cosine? Sebastian, is that you? Say again. Yes. Oh, I don't know if you said cosine or cosecant. Sine of theta is equal to 1 over the cosecant of theta. And that makes sense because we know they're reciprocals of each other. So instead of reciprocating the 1 over y, we can literally reciprocate the cosecant itself. Similarly, cosine of theta can be defined as what? Very good. 1 over secant of theta. And then the tangent of theta can be defined as 1 over cotangent of theta. And then the other 3 can be flipped as well. So again, I'm going to write them real fast and I'll let the screen blink and then you can write everything. We know the cosecant of theta is 1 over sine of theta. Secant of theta is 1 over cosine. And then cotangent is 1 over tangent of theta. So these are your first 6 identities, or the first 6 reciprocal identities. Those are the only reciprocal ones. Okay, now we're going to use what we know about the definitions of our trig functions to come up with 2 quotient identities. Now, Matthew, you actually hinted to this earlier. Tangent of theta is defined as y over x, but y and x are also defined by something else. How else can I rewrite this? Yeah, sine of theta over cosine of theta. So then if you skip from, or if you just skip this middle step, then we found our first quotient identity, which, so you can write this on your orange sheets. The tangent of theta is equal to sine of theta over the cosine of theta. So there's your first quotient identity. We have 2. What if I reciprocate both sides of this? What's the reciprocal of tangent? cotangent. And if I reciprocate sine over cosine, then I get cosine over sine. So these two are your quotient identities. Any questions so far? Okay. Okay, next we're going to do some Pythagorean identities. So go back to your notes because I want you to be able to work this out in your notes before we write the identities on your orange sheet. Let's sketch out a small first quadrant. So in the first quadrant, and we'll just put any point on the circle. And remember, if something is an identity, it works for every angle no matter what. So I don't want to actually put specific coordinate points like square root of 3 over 2. Like square root of 3 over 2 and 1/2 and all that kind of good stuff because I'm trying to prove this works for every single one. So if I have this coordinate here, again, this is the unit circle. And I can make a right triangle. And I've got a central angle theta. Can you help me label the sides of this right triangle? Not using numbers. Would be what? Yes, but the hypotenuse is something even easier. And I say not to use numbers, but you're allowed to use a number for that one. Because in the unit circle, yeah, we know the hypotenuse is 1. Yeah, right? It goes y up from the x-axis, and then the adjacent side would then have to be x. Yeah, that's all. I know. It's a lot easier question than you may have realized that I was trying to ask. Okay, so now, what does the Pythagorean theorem say about this triangle? X squared plus y squared is equal to 1. Now, you can write x squared differently. Say again? Yes, but let's use trig functions. That's it. Well, x squared is cosine, right? So cosine squared theta plus, so it works, so even though x is cosine, that means x squared is cosine squared. Okay, and then y squared will be sine squared y equals 1. Okay, on your orange reference sheets, typically we see it written this way first. Why did I put sine of y? Hold on, my brain went ahead of itself. This should be sine of theta. So typically in the identities, and maybe just because it rolls off the tongue easier, I don't know. Wake up, wake up. Hold on, my computer's freaking out a little bit. All right, so sine squared theta. So sine squared theta plus cosine squared theta is equal to 1. This is your first trig identity. We have 3. I'm coming. Can you see it now? Okay, so there's the first. Now, to get the second, I want you to suppose we divide all 3 of these terms, divide every term by sine squared theta. Okay, if we do that, what happens? What is sine squared theta divided by sine squared theta? 1 plus, what is cosine squared theta over sine squared theta? Look, Close. Cotangent squared theta. And then what is 1 over sine squared theta? Cosecant squared theta. Very good. So you see how we're using our other definitions and our other identities to create more identities. And we're using algebraic properties to derive them. Uh-oh. Bless you. That was very loud in my ear. It's okay. I forgive you. Okay, now let's do, we have one more. So now if we take sine squared theta plus cosine squared theta equals 1, and instead of dividing every term by sine squared theta, let's divide every term by cosine squared theta. Okay, so if we do that, what is sine squared theta divided by cosine squared theta? Tangent squared theta. Plus cosine squared over cosine squared is 1. And then what is 1 over cosine squared? Secant squared theta. So this is your third Pythagorean identity. The last identity we're going to put on our orange sheet today is called opposite angle identities. Identities. Okay, and I'm not going to take the time to derive it like we did the others, just because we don't use it as much for what we're doing, but just so you have it in the event that we do need it. Basically, it has to do with the fact that, well, let me write it. The first one is this: sine of negative a is equal to negative sine of a. And I could have put theta, but that's okay. Sine of negative a is equal to negative sine of a. So what this means is your sine value or your sine function deals with the y values. So think about, like, in the first quadrant, your y value is always positive, right? Or let's do fourth quadrant rather. In the fourth quadrant, your y value is always negative. So it doesn't matter if your angle is negative or if you negate the sign, whether negative is inside or outside, they will be equivalent to one another. Cosine deals with the x value. It's a little bit different. The cosine of negative a is equal to positive cosine of a, and it has to deal with our x values. And right, think about x values are both positive in the first and the fourth quadrant. So whether that angle is positive or negative, its cosine will always be positive. So these are the only two opposite angle identities. Okay, any questions so far? Okay, that's where the identities are going to stop, but now here's why we're learning them and how we're going to use them. So, for our examples, you're going to use trig identities to find the exact trig value. Use trig identities to find the exact trig value. Previous to today, this question was phrased differently. You got the question that said, use what you know about the unit circle to find the exact trig value. So since we derived our identities from the unit circle, though, we can kind of use those as a different means of setting it up. Now, here's the catch. Not the catch. This is the goal. This is going to be the thing that's going to help you. Your goal is to find one or maybe more trig identity that relates the given ratio to the ratio we need to find. Find one or maybe more trig identity that relates the given ratio to the ratio we need to find. And I'm going to take you through 3 examples of how to do this. Okay, if you've zoned out on me, this would be a great place to zone back in. So here's what it looks like. Given that the tangent of theta is the square root of 3 over 4, and that theta must be between 0 and pi over 2, I want you to find the cotangent of theta. Now, this one's a very, very easy problem. I hope you see that, but I'm going to take you through kind of the mindset that you should have when solving this so that you know how to solve the more complicated ones. The first thing I want you to do every single time is to figure out what quadrant you're dealing with. And that's going to be from this given piece of information. Where is theta between 0 and pi over 2? What quadrant? The first quadrant. So quadrant 1. Now, what's important about this is that the given ratio must be satisfied in quadrant 1, and your answer must be satisfied in quadrant 1. So what I mean by that is you can't have an answer that is outside of that quadrant. So can you have a negative cosine value in quadrant 1? No, right? Because cosine deals with x's, and in quadrant 1, all of your x's are positive, right? So, this is positive, positive. This is negative, positive. This one's negative, negative. This one's positive, negative. So in the first quadrant, everything is positive. Now, tell me about tangent and cotangent. Well, in quadrant 1, can you have a negative tangent? How? But in quadrant 1, can I ever have an x and a y that are negative? Yeah, in quadrant 1. In quadrant 3, I do have both negatives, but is the tangent negative in quadrant 3? No, because I'll still have a positive. And guys, remember, if you think tangent in terms of slope, you will have positive lines in the first and the third quadrant, and you will have negative slopes in the second and the fourth because those lines have to go through the origin. So that's one way to think about it. All right, so use my suggestion. Can you tell me of a trig identity? So this is going to be where you're going to reference your orange sheet. Can you find a trig identity that relates tangent to cotangent? And if so, what is it? Say again, Zach. Okay, so tangent of theta is equal to 1 over cotangent of theta. You also could use cotangent of theta equals 1 over tangent. So it doesn't matter which one you use. The thing about identities is that they work, algebraically. So as long as you use them appropriately, we should all get to the same answer no matter what. So let's plug in what we know. We know the tangent of theta is the square root of 3 over 4. And that's equal to 1 over, we don't know the cotangent of theta. Okay, but I need to solve for the cotangent of theta. So how can I do that? Okay, so if I multiply both sides by the cotangent, then I end up with, let's see, so this implies that the square root of 3 over 4 times the cotangent is equal to 1. And then how can I get cotangent alone? Divide both sides by square root of 3 over 4. And then what do you get for the value of cotangent? 4 over the square root of 3, right? It's just the reciprocal. But then you have to simplify this by rationalizing your denominator. And then when you multiply straight across, you end up, or you should end up with, that the cotangent of theta is going to be 4 square roots of 3 over 3. Now, before you circle your answer, your box your answer, you need to check. We are in quadrant 1. So is this okay in quadrant 1 to have this value? So in quadrant 1, can we have is cotangent positive or negative? It's got to be positive because cotangent is x over y, and my x's and y's are both positive, so this is good. So that's why this one is your answer. Now, I'll give you a hint, Zach. Had you picked the other one, had you just done cotangent of theta equals 1 over tangent, it was going to be a lot fewer steps. And so that's the deal with doing this. And when we get to proofs here in a couple days, there are a ridiculous amount of ways for you to prove things. One, no more right than the other. But it just kind of depends on what your brain sees and what you decide to go with, so to speak. And so the best thing to do too is not kind of be swayed by, looking for the one correct answer, because they're going to be this example we could probably do in a couple of different ways too. But the third example that we're going to get to, I did it one way myself. First period came up with a second way. Third period came up with a third way. So very quickly, it kind of developed into multiple options, and it just kind of depends on how your brain works and what trig identities you want to use. All right, example 2. Given that the secant of theta is equal to negative 5/4, and that theta is between 90 and 180 degrees, I want you to find the tangent of theta. What quadrant are we dealing with here? The second, right? Between 90 and 180 degrees. So we're in quadrant 2. Okay, look at your identity chart. Can you tell me of a trig identity, or a few maybe, that have a relationship with secant and tangent? Tangent squared theta plus 1 equals secant squared theta. Okay, so let's substitute in what we know. We don't know tangent, so we'll leave that alone. But we do know secant. We're given that the secant is negative 5/4. So I can plug in negative 5/4, but it's secant squared. So this would be negative 5/4 squared. So again, we just use algebra properties to simplify. We're trying to solve for the tangent of theta. So I'm going to leave tangent squared theta alone for now. Plus 1 equals, what is negative 5/4 squared? Did you say negative? Right. Right, negative times the negatives are positive, right? Okay, and then to isolate tangent squared theta, we need to subtract 1 from both sides. So then tangent squared theta, 25/16 minus 16/16 is how many sixteenths? How many? Awesome. And then how do you suppose we might isolate tangent of theta? Yeah, we can take the square root of both sides. So then we get that the tangent of theta, what do you need to remember when you take the square root? Is plus or minus the square root of 9/16. Now, what is the square root of 9/16? 3/4. So this is also plus or minus 3/4. Okay, so it is at this point where we have a different scenario than the first question. Now you have a choice of, is it plus or minus? Well, go back up to our stipulations. This angle needed to be in quadrant 2. So we need to know in quadrant 2, is tangent positive or negative? It's going to be negative, right? I have slopes of negative, my lines have slopes of negative, whatever they may be, in quadrant 2. Therefore, the tangent of theta is going to equal negative 3/4. Guys, if this kind of weirds you out, just go back to the chart up here that I drew where all the signs are, and tangent's found by doing y over x, right? So if I have in quadrant 2, the y values are positive, y over x. Y values are positive, x values are negative. When you divide a positive divided by a negative, you get a negative. So that's why the answer is negative 3/4. Any questions about that? Okay, last example. Number 3. Given that the cosine of theta is equal to 1/8, and we got 3 pi over 2 is less than theta is less than 2 pi, I want you to find the tangent of theta. So your job, your goal, is to try to find a trig value that relates cosine to tangent. So you could use that one, Zach, but the issue is it's not a direct relationship, right? Like if we do that, then we're gonna have to be dealing with something with sine. So here's the issue. There is no direct, there is no identity with direct relationship between cosine and tangent. So when that happens, and this is what we typed up at the top under our goal, sometimes you want to find one, sometimes you have to find more. So what we're going to have to do is we're going to have to find an intermittent trig function. So we're going to go from cosine to something else, and then finally to tangent. So you need to find basically one identity that's related to cosine, or one trig function that's related to cosine in an identity, and then that same one that's also related to tangent. And this is the question that I did 3 times. So there are multiple ways that you could approach this. Yeah, so what Zach has suggested, and so you have 2 options. The first time I did it, I did sine as my intermittent trig function, but if you actually do secant as the middle one, I guess I could write it here, huh? Then you'll actually get to it with a lot easier algebra. Haha. Okay, so what's the first one that we'll use? What kind of relationship does cosine and secant have? Give me an identity. Cosine theta is equal to 1 over secant theta. So we can substitute in what we know. We know cosine theta is 1/8. So then we're going to have 1/8 equals 1 over secant of theta. So how can we solve for secant of theta? What do you? Oh, yeah. Okay, so mathematically speaking, we can maybe cross multiply. So you could do that, Tyler, then you'd get like 1 divided by 1/8. If you cross multiply, you actually get your answer right away though, because then 1 times secant theta is secant theta, and then 8 times 1 is 8. So in one step, you get secant of theta is equal to 8. Yeah, and it's how your brain wants to think about it. Okay, now what what identity relates secant to tangent? So Zach, you said it earlier. Okay, so then let's substitute what we know. Tangent squared theta is going to hang out, plus 1 equals secant squared theta. We know secant is 8. So the only place that might catch you off guard, or the only thing that might catch you off guard, is you have to make sure that you square that. 8 squared. And then, so then 8 squared is 64. And then if we subtract 1 from both sides, then we get tangent squared theta equals 63. Then what? Okay, so then tangent of theta equals plus or minus square root of 63, which is not simplified. 3 root 7, right? Because this is the square root of 9 times the square root of 7. And the square root of 9 is 3. So 3 square root of 7. So again, you've got plus or minus, and you need to decide in, did I even talk about the quadrant? No. What quadrant is between 3 pi over 2 and 2 pi? Quadrant 4. So in the fourth quadrant, is tangent positive or negative? Tangent must be negative in the fourth quadrant. Therefore, my computer's really slow, sorry, so it's affecting my scrolling. Okay, therefore, the tangent of theta is equal to negative 3 square roots of 7. Is this making sense so far? Who's hurt? Esme, is that you? Who's on crutches? Or Ashley? Okay. I was like, what did Esme do? Ashley, are you feeling better at all? That's good. Yes.